Hello, in this video I'm going to solve a problem for you on the topic of modular arithmetic. Determine the remainder of this number by 17. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. If you do the calculations correctly, the answer to the problem is 11. The interested audience can refer to the following playlist for similar problems. The link to the PDF file that you can see on the display right now is in the description below the video. Okay, my goal is to find the remainder of the division of this very huge number by 17. So in the modular arithmetic language, it means that I have to simplify my number in module 17 and reach to a number so that that number is an integer between 0 up to at most 16. If I could do this, if I can't do that, then of course this number will be the answer to the problem. But before starting the problem, let me explain a little bit about these consecutive exponents that appear. So in math, we have two notations. Yes, we have a to the m to the n, and we also have a to the m to the n. Okay, there's a very big difference between them. So if I ask you what this is, you will tell me this is a power. If I ask you what this is, you will also tell me this is a power. But if I ask you what is the base of this power, you will tell me m to the mth is the base and n is the exponent. If I ask you here what the base is, you will tell me a is the base and the exponent is m to the nth. In other words, the base here is another power. The exponent is just a simple number n. Here, the base is a simple number a, but the exponent is another power. In other words, here we do not put any pairs of brackets, but if I want to put a pair of brackets, I have to prioritize this operation first. Okay? And there is a very big difference, of course. For example, if I tell you 2 to the power of 2 to the power of 3, you know how to calculate this. The famous rule of power tells me that I can multiply the exponents. So this becomes 2 to the 6, and it becomes 64. But if I ask you what 2 to the 2 to the 3 is, you have to prioritize this operation. It means that I have to calculate 2 to the third first, which is 8, and then this becomes 2 to the 8, which becomes 256, and then there is a huge difference between them, of course. Okay, so this is of this type, yes? Because I have consecutive powers without any pairs of brackets around them. Okay, so if I want to solve the problem, something which is a little bit, let me simplify the problem. This is, of course, a known given number, but this is so huge that I can say that I really don't know anything about it. So for the time being, to simplify the problem, if you don't mind, let me call it n, and then I bring the problem down, and 6 to the n, I want to simplify it module 17. Okay, but then you usually, if you have followed my lessons, you know that we have to find an ideal case. Yes, I want to find, if possible, some power of 6 which is congruent to either 0, 1, or minus 1, module 17, because 0, 1, and minus 1, which I call them the ideal cases, are the only numbers that I can raise them to high powers without any problems, without calculator. Yes, 0 to any power, no matter how huge is that, is just 0. 1 to any power is just 1. Minus 1 to any power, if that power is odd, it becomes minus 1. If that's even, it becomes 1. So these are the numbers that I can raise them to high, extremely high powers very simply. So that's why I call them ideal cases. Okay, so what we want to do, this is my recommendation. So for example, you go to a scratch paper, this is the way that I think, okay? You don't have to write them down, but this is the way that I think. So I will have two columns. One column, I will write the powers of 6 as much as I can. Of course, it immediately goes beyond my calculation of power without calculator, but of course, 6 to power 1 is 6. 6 to power 2 is 36. I also can calculate 6 to power 3, 216, but let us not continue it like that, because it becomes extremely big numbers. And on the other column, I will write multiples of my module. So 17 is the first multiple, the second one 2 times 17, 34, the next one 3 times 17, 51, and this list also continues forever. I mean, I will investigate a few of them as much as I can and then try to look for the ideal case. I ask myself, is it possible to find a number on this list so that it differs by any number on this list by 1 unit, either one more or one less? Or is it, I'm so lucky that one of them is exactly this? Because if one of them is exactly that number, this means that power of 6 will be congruent to 0 in the module. Okay, but as you see, as far as you see, the ideal scenario is not happening, but then I will look for the minimal distance. I hope that you agree with me, the minimal distance occurs here, okay? And this is 36 and 34. So it means that I could not find the ideal scenario so easily. If the problem is so simple, you usually immediately can find that ideal scenario. If the problem is a little bit higher level, you need to gradually reach to the ideal scenario. Okay, so I was not able to find that, so I will put the base of my calculation, the second power of 6, which has the minimal distance from one of these multiples. Okay, so let us start from here. I would say that, okay, 6 to power 2, I want to simplify module 17. Extremely simple, it is 2y. 36 minus 2 is 34, and 34 is a multiple of 17, so it is divisible by 17, so that's true. But now, what happens? Of course, I want to raise it to high powers, but for example, if I raise the left-hand side to power 100, say, it becomes 6 to the power of 200. The right-hand side becomes 2 to the power of 100, yes? So 6 to the power 200 is, of course, much bigger than 2 to the power of 100. But for me, it doesn't matter, because 2 to the power of 100 is also outside the realm of my calculational power, okay? So it's not still good. So what I will do, it's not very hard, hopefully, to see if you are especially good with numbers. Then if I raise this to power 4, what will happen? This becomes 6 to the power of 2 to the power of 4. Then I will have my ideal case, because this becomes 2 to the power of 4 module 17, but 2 to the power 4 is nothing except 16, and 16 has the ideal name, module 17, which is minus 1. Do you see why? Because 16 minus 1 is 17, and 17 is divisible by 17. So, on the other hand, 6 to power 2 to power 4 is just simply 6 to power 8, and then I have minus 1 and then 17 here. Okay, so I have my ideal scenario, because I told you I want to have a power of 6, which is either 1 or minus 1 or 0. Of course, 0 cannot happen here. So this is my ideal scenario. So I couldn't, it was very hard for me to continue this list and see that, okay, when I reach to the 8th power, I have this ideal scenario. But I can still do a little bit better, because minus 1 is also somehow problematic, because when I want to raise it to some power, I have to know if the power is odd or even. So to prevent that to happen, so let me just raise it to power 2, and make it positive. So this becomes 6 to power 16, because if I raise it to power 2, it becomes 6 to power 16. If I raise it to power 2, it becomes 1 module 17, and I have my ideal case here. Okay, for the people who know number theory in a little bit more advanced level, they could immediately write that, not by this trick, by the so-called little Fermat's theorem. So let me just mention what is little Fermat, what is the little theorem of Fermat. So if A is a natural number and P a prime, so that GCD, the greatest common divisor of A and P, is 1, it means that A and P are relatively prime or co-prime numbers, then Fermat was able to show that A to the power of P minus 1, this prime number 1 unit less, is congruent to 1 module the prime number. Extremely beautiful and simple theorem. Statement of the theorem is very simple. So for example, if you are working on a little bit advanced level in number theory and you knew about this theorem, you can immediately exploit this here. Why? Because this module 17 is a prime number. So if I knew about this, what could I say? I would say that let me give the rule of a to 16. Give it to 6, and let me choose p to be 17. I know that 17 is a prime number. I know that 6 is a natural number. On the other hand, if I ask you what is the GCD between 16 and 17, you immediately see that is 1. Then you can conclude that a to the power of p minus 1, p is 17 minus 1, is congruent to 1. Sorry, a is 6 here, is congruent to 1 module 17. But this is 6 to power 16 is congruent to 1 module 17. So the people who know actually number theory in a more advanced level, they could immediately write this, not by this trick, by Fermat's little theorem. Anyway, we have it now. So let me write it here. 6 to power 16 is congruent to 1 module 17. But now I have to come close to this huge number. What should I do? So I have to ask myself, I need to raise this to some power and this to some power so that when this exponent is multiplied by 16, it becomes as close as possible to this huge number. And of course, 1 to the question mark is always 1. But the problem is that because this number itself is so huge, I don't have any clue how big number is, so I don't know how many multiples of 16 I can fit here. Because you know that if the question mark is multiplied by 16, the exponent becomes a multiple of 16. So how many 16s I can fit here, I don't know. But we know what to do in modular arithmetic, so it means that it motivates me to start simplifying that huge exponent in module 16. Okay? Because I want to know how many multiples of 16 I can fit here. Okay, so let us do that. Here, this number is above my module. Whenever this happens, that a base number, a number in the base, is bigger than the module, simplify it. So 19 can be viewed as just 3. Yes, because 19 minus 3 is 16, and 16 is divisible by 16. So I replace 19 with 3, and I copy and paste the exponent. Okay, but now can I have the ideal scenario? For example, you see that Fermat's little theorem is useless for this case, because now my module is 16, and 16 is not a prime number. So I have to somehow go back here. So I need to ask myself, is it possible that any power of 3 become 1 unit more or 1 unit less than a multiple of 16? I mean, it is not very hard to see that, yes? Because if you continue this trick, when you reach to 3 to power 4, it becomes 81. And if you start continuing multiples of 16, at some point you write to 80. It's 5 times 16, and then I get my ideal case. So it motivates me to put the base of my calculations the 4th power of 3. So what do I do here? I will continue. Instead of this, I would write 3 to power 4. Then I ask myself, what number should I put here so that I become as close as possible to this exponent, but I am not allowed to go beyond because division is not allowed. So I will write, I think, 44. 4 times 44 is 176. I need 2 more, so I multiply by 3 to power 2. But 3 to power 4 is 81. 81 in module 16 is just 1, because 81 minus 1 is 80, and 80 is divisible by 16. So I continue. Instead of 3 to power 4, I simply put 1. I copy and paste the exponent, and then 3 to power 2 is just 9. and then 1 to power 44 is 1, so this becomes simply 9. Okay, so this means that this number is congruent to 9 when it comes to module 16. What does it mean? It means that it is a multiple of 16 plus 9 because its remainder is 9. Okay, so let me explain it a little bit better for you. So here, I realize that 19 to the power of 178 is congruent to 9 module 16. By the very definition of congruency, this means the number on the left minus the number on the right is a multiple of 16. This is the definition of congruency. So it means that I can write it as 16 times q, for example, where q is an integer. Okay, so what happens then? This means that 9 to the power of 178 is a multiple of 16. Which multiple I don't know, but plus 9 units. So and q is an integer. So this is what I know. But then you will see that even if you don't know what q is, you can solve the problem. So that is the idea. You have to have this experience and remember it for similar problems. So let us try to glue everything now together. Okay, so let me clean this board. Okay, so now what do we have? Let us glue them to one problem here. So here I got this, that 16 to the power of, 6 to power 16 was congruent to 1 module 17, okay? And I also learned that 19 to the power of 178 is a multiple of 16, which multiple I don't know, but plus 9. And this is important that q is an integer. Of course, here q is a natural number because all of the numbers are positive. Okay, so what I will do, I will go back to my main problem. So what I will do, I will do this. 6 to the power of 19 to the power of 78, which was my original problem, and my goal was to simplify it in module 17. I can replace this with that combination. So here I know that q is a natural number, but I don't know what that is. So I would write it as 6 to the power of 16q plus 9. Yes? And then here I can write it as 6 to power 16 to power q, yes, multiplied by 6 to power 9. Yes, because 16 times q is 16q, and then I will write it in this form. That's correct. But 6 to power 16 module 17 is just simply 1. So this becomes 1 to power q multiplied by 6 to power 9. Yes? And 1 to power q is just simply 1. So the answer becomes just a 6 to power 9 module 17. Okay? So it was a very good progress. Yes, I was able to show that 6 to the power of 19 to the power of 178 is congruent just to 6 to power 9 module 17. Okay, but this is not acceptable, even though it is a very small number compared to this one, but it is not acceptable because I have to have this condition as well. But now look, I had this before, yes? 6 to power 8 is minus 1 module 17. This is 6 to power 9. So it is very simple to decompose it to 6 to power 8 times another 6 module 17. But 6 to power 8 is just simply minus 1, and then it becomes minus 6. But minus 6 is also not acceptable because it should be non-negative. But there is another name for it, and that name is eventually 11. Okay, so finally the problem is finished. I was able to simplify this by this long process to 11 module 17. Okay? By the way, don't think that if you have calculator available, because I remember I put this number in Wolfram Alpha, So it was beyond the memory of the system. Even I have access to the premium of Mathematica, so my computer didn't have enough memory to calculate this, because if you have access to softwares, if you want to do that, for example, in Mathematica, you can write mod, and then you can type this number there, and then write 17 here. But even if you have one of the best softwares available, it was not easy just to calculate it without having these ideas. I mean, even if you have calculator handy, don't think that you could solve this problem with the calculator. But anyway, I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.